we're learning about cross products. This is yet another lesson about vectors, and essentially we will learn about dot products. This is a notation for dot products. Cross products are like this, so you just put a cross there. So what do you do? So firstly, it only applies to, R3. So what do I mean by this? Basically, I mean that vector A and vector B both have to be three-dimensional. So like this. So XA, you know what, I'll just do, so they have to have three components, which are all real numbers. So A1, A2, A3 times B1, B2, B3. They can only apply, so cross products only apply in R3. So what do you actually do? You look at the first, so you do this dimension by dimension. You look at the first component and you ignore the first row here. You look at the second row. So you look at the second and third row. You go A2 times B3 minus A3 times B2. That's the first component of our new 3D vector. The second component, you ignore the second row. We're really tempted to do A1 times B3 minus A3 times B1. But the exact process is the opposite. So we take the negative of this. We have A3 times B1 minus A1 times B3. And then for the third component, we essentially just ignore the third row. Then we take A1 times B2. Again, we do the same thing as what we did in the first row. We have A2 minus B1. So this is essentially what we do in cross products. So now let's just work through a few examples so you can hopefully get more familiar with this system, because the system is kind of weird. Okay, so example 1. Let's say I had vector A is 3, 4, negative 2. Vector B is 1, negative 6, 5. I'm going to go ahead and find the cross product of these two vectors. The result will be, so for the first dimension, we ignore the first row. And we have 4 times 5. So we have 4 times 5 minus negative 2 times negative 6. So that's essentially what we were meant to do for the first component of our new vector. And then for the second component, we ignore the second row. We have, then we take negative 2 times 1, so A3 times B1, minus 3 times 5. For the third component, we ignore the third row. So like this. And then we have 3 times, so we do the same thing again as the first row. We do 3 times negative 6 minus 4 times 1. This is going to be our resulting vector. So let's just evaluate that. Evaluate this so we get 3 real numbers, not these brackets multiplied together. So if we evaluate this, will result in, so we have 20 minus 12, right? 20 minus 12, negative 2 minus 15, negative 18 minus 4. So essentially this is again equal to, so if we evaluate this, we have 8, negative 17, and negative 22. So 8, negative 17, and negative 22. So this is the first example. Let's look at another example. We have let's say we had 8, 5, negative 4 times, or cross product, 9, actually negative 9, negative 6, and 3. So what we're going to do here is just try to pause this video and do this without going back and looking at how we actually do the cross product. Assuming you pause the video, let's just try the answer. So we ignore the first row and we have 5 times 3 minus negative 4 times negative 6. So 5 times 3 minus negative 4 times negative 6. Then for the second component, we ignore the second row. We go 8, so we go negative 9, actually negative 4 times negative 9 minus 8 times 3. For the third component, we ignore the third row. We go 8 times negative 6 minus 5 times negative 9, like this. Okay. So we just evaluate that. Then we get 15 minus 24. Yeah, 15 minus 24, 36 minus 24. And then negative 48 plus 45. So we evaluate this, we get negative 9, 12, and negative 3. So that's going to be our answer, I believe. So now, let's just talk about an interesting property and also useful property of cross products. Essentially, that is vector A, the cross product of vector A and B is orthogonal to both vector A and B. So what do I mean by orthogonal? Orthogonal essentially just means perpendicular. And how is this possible? That any random vector A and B has this new vector that is perpendicular to both of them. Well, don't forget that we're in a 3D coordinate system. So essentially what this means is, so I'm going to draw this 3D coordinate system. This is Z. This is Y. And then this is X. So let's say I'm going to just draw vector A over here, so vector A. And then we have vector B. So essentially what it means by having something orthogonal to both vector A and B is just, so we have this plane where both vector A and vector B are on this plane. So essentially this plane is going to be something kind of slanted like this. Something like this, and it's like slanted like that. So essentially we have a plane like this. So just imagine that this is like a 2D plane. Imagine that this is like a 2D plane that cuts through the coordinate system of the 3D coordinate system. It's 2D and the two vectors are on this. So this actually goes through the origin because the two vector lines are on this. So just these two lines are actually on this plane. Okay, so now being orthogonal, so let's just imagine we have a vector that is orthogonal to the plane. So if a vector is orthogonal to the plane, let's say it's like this, right? Let's just imagine it's going this direction. So wait, something like that, and let's just say it's orthogonal or perpendicular to the plane. So if you tilt your head around, then you get something like this line here, this vector here is orthogonal to this plane, or this kind of 2D shape below it. So something like that. So this is how this works, and let's just try to prove this concept, that if we have vectors A and B, the cross product of these two vectors are orthogonal to both vector A and vector B. So we have both vector A and vector B. Vector A and vector B. Let's just say vector A is A1, A2, A3. Vector B is B1, B2, B3. So essentially we know that the product of the two vectors, will be so we have A2, B3 minus A3, B2, A3, B1 minus A1, B3. Then we also have A1, B2 minus A2, B1. So why am I writing vector A and the cross product of vector A and B together? Because if these two are orthogonal, then their dot product should be equal to 0. So how do we calculate the dot product? Well, this is essentially just so A1 times A2, B3 minus A3, B2. Then, so this is going to be equal to, and then if we just add that to, so we plus A2 times A3, B1 minus A1, B3. We again add that to A3 times A1, B2 minus A2 times B1. And this should be equal to 0. So it is equal to 0, and let me just expand this to show you how. So this is just going to be equal to A1, A2, B3 minus A1, B2, A3 plus A1 plus B1, A2, A3 minus A1, A2, B3 plus A1, B2, A3 minus B1, A2, A3. So as you can see, we can cancel out terms out from each other, because B1 times A2 times A3 has a plus or minus term, and then this has a plus or minus term, and this has a plus or minus term. So we are left with nothing left, and we have 0. This essentially means that vector A is orthogonal to the cross product of vector A and vector B. You can prove that vector B and the cross product of vector A and B are orthogonal the same way. So thanks for watching.